I am.
So, Mr. Williams has done many things. Right now he works for the University and the College of Business with fundraising, but he has a passion for mathematics and going back in the history of mathematics, which some of you are appreciating with Dr. Anderson right now, or have recently. So I will, he said this ordinarily takes 3 2-hour sessions. So we're going to split you into groups.
But this is an advanced group.
But you guys know what's going on. So he is going to go till 2 o'clock. I'm going to give him a 10 till 2. And you tell me which of these you want to.
Okay. Well, first of all, let me tell you how much I appreciate the opportunity to share this with you. I have been giving variations of this program for over 20 years to absolutely no benefit to anyone. A few weeks ago, I ran across a way of presenting it that I think will be much more effective, and I've done it. You're the 4th group I've done it with, and the response has been great. So I'm interested in your feedback, and I'm also interested in hearing from you and your teachers how far we can push this down. I'm targeting 5th grade, and I want to know if that's possible after we finish. Now, you can get the sheet of paper I told you not to look at. Let me tell you how I think about life and how I go about learning things. First of all, I was not born in Commerce. I got here when I was 3 years old. I started 1st grade, and I finished college here. So that's kind of an odd thing. Most people say, well, bless your heart, you don't know anything. Never left town. Spent 40 years in a retail car business here in town. 5 years ago, I became a fundraiser for the College of Business, and I am an amateur geometer. What is a professional geometer? You ever seen one of these? What is this? What is it? What is it? Everyone who you describe as a carpenter is a professional geometer. You should think about bringing them into your classroom. They can teach like crazy because they know what? Right angles. That's what we build, isn't it? Professional geometry. All right. Looking back to move forward. That's all we're doing. We're looking way back to move forward. Ignorance breeds arrogance. I can't know what I don't know. I must learn before I speak. I must remain curious. Keep that in mind for the rest of your life. Okay, we're going to go back in time. We're going to go back to the time of the Pythagoreans. When did Pythagoras live? We know that theorem, but where did it come from? When did he live? Where did he live? You got to be curious to know when he lived. About 500 years before the Christian era. Yeah, 2,500 years ago. What I have done is dusted off some of the simplicity that the Pythagoreans taught. That Pythagoras taught them, and then this was a group. This was a weird group. It was a religious cult, and they had secrets. And a way I think we're going to approach 5th graders is this. Can you keep a secret? Can you keep a secret? Sure? Can you? All right. Now, if you can't, you're going to need to leave. Is that all right? Okay, you got it. You got to have a secret. Now, you can talk to any adult about this that you want to, but you cannot talk to your fellow students. Is that okay? Can you keep a secret? You sure? All right. Because here's the secret. I'm not going to show it to you yet. All right, 5th graders might get engaged if you play a little game with them, because what you're going to show them is almost magical and simple, and they can understand it. I want you to take the sheet. This is called the Square One Academy. The pretty picture you see there is what you're going to make. The emblem is what you result in. What you're going to do is harmonize square one. You're going to double it, triple it, quadruple it, and quintuple it with 7 paper plates. And you're going to know how it happens. And we're not going to talk about math. Isn't that something? We're just going to do it. We're geometers. We don't have numerals at 500 BC. Did you know that? Romans, you can do Roman numerals, right? You do long division with Roman numerals? Why? Huh? Do you? Do you? Have you done long division with Roman numerals? Is it fun? What's it missing? Does it have a zero? Does it have a decimal? Does it have place value? No. Well, wait a minute. We're talking about Hindu Arabic numbers. Why do I call them Hindu Arabic numbers? Pardon? Who did? Who did? Where did those things come from? We use them every day. That's the only gateway to math, right? Hindu Arabic numbers. When were they invented? Looking back to move forward, we got to get curious about where these things started and what tools were available when. Because we're going back to the Greeks, and they left us some wonderful things in art, architecture, and sculpture. How did they do it without numerals? Blank faces. What'd they do?
They used the alphabet for a numeral system.
Absolutely. They assign numeric value to the alphabet. Now that's really easy to do long division with, isn't it? The names had numeric value. And that's important to remember. But they didn't have the manipulation of ratios that you and I are familiar with, and that's the way we started math. So we're going back. We're going back 1,300 years before Hindu Arabic numbers were even thought of. They were about 800 AD in India, and it took about 500 years for them to get to Europe. And it took about 300 more years for them to become popular. So what we're going to do today, this big secret, has to do with the simplicity of what the Greeks did to teach how do you harmonize from square one, and what does that have to do with music? How many musicians do we have? What do you play? Violin. Oh, we like strings. What do you?
Bass.
Bass, more strings. What else? What? Pardon?
Piano.
Pianos, more strings. We're gonna do some strings. Cello, we got more strings. Okay, you're gonna enjoy the relationship of visual harmony and auditory harmony because it comes from the same place, and it's simple. What the Greeks used, 3 devices is all they had. It's all they needed: a compass, a straight edge, a marking device. Have you ever heard that before? That's all it took to harmonize every beautiful structure they left us. Have you ever heard that before? Oh, it's so simple it hurts. Now you've heard it. We're looking back to move forward. Now, when did I hear it? 7 liberal arts. Can you name them? What's a liberal art?
Everything not science.
Do what?
Everything not science.
Everything not science? Elder guesses? What? There are 7 subjects that for 2,000 years were not changed into the backbone of Western civilization's education, and we forgot to tell you. There were 7 subjects. What were they?
Art, music, philosophy.
Art, music, philosophy. Anybody else got some more? Law. What else? Well, you can look on that board and read them. The trivium, 3 roads crossing, was grammar, rhetoric, logic. The quadrivium was arithmetic, geometry, music, and astronomy. 500 BC. What are we calling arithmetic with no numerals? Won't sell, will it? What does that mean? Arithmetic, 500 BC, meant the meaning of number. There were no numerals to manipulate, so we got to redefine it. Geometry. Was geometry, is geometry, forever will be geometry without change. It's the same. Music. Astronomy. Why are those 4 subjects for math? You musicians know? What does harmony come from? Pardon?
Numbers.
It comes from proportions. Proportions. All right, the quadrivium is 4 roads crossing. Arithmetic is number in itself. Geometry is number in space, 3 dimensions. Music is number in time. Astronomy is number in space and time. Is that calculus? I never had it. I don't know. Is that what it is? Okay. Grammar, rhetoric, logic, arithmetic, geometry, music, and astronomy. Where did I first hear that? I was 21 years old when I became a Freemason. Grammar, rhetoric, logic, arithmetic, geometry, music, and astronomy. This is a winding stairway of the 2nd degree in Freemasonry called the Fellow Crafts degree, a fellow of the craft, above the entered apprentice. Freemasonry is the symbolic building of King Solomon's temple that you get in the Old Testament. And part of it is walking a winding stairway of 3, 5, and 7 steps. The 7 steps are grammar, rhetoric, logic, arithmetic, geometry, music, astronomy. 21 years old, I see that, and I say, now I know what all that is, but this degree was made back in, goodness, in the early 1700s in England. Why did they do that? And I've spent every minute since then wondering. And I found out a whole lot about it. Not enough, but a whole lot. But I did learn that those 7 subjects was what made Western civilization better than any other during the time period. Better at what? Industry, and especially military, and navigation, Navy. That's the reason that Western civilization kept, on the adventuring, they kept ahead of everybody else. All right. That's how I got it. Show that other picture. The founders of our country tended to be Freemasons. This is George Washington in his role as master of his lodge, setting the cornerstone on the White House. I'm sorry, that's the Capitol building, which they've never found that cornerstone. He was a surveyor. What does geometry mean? Geometry. What's that mean? Geographic, geometric, what? It looks like those globes, doesn't it? Geo, it means globe, world, ground, earth. What's geology? Metry, what's that mean?
Measure.
Earth measure, surveying, you got it. George Washington was a surveyor, a geometer by profession, one who looked back to move forward. The founders of our country looked back to Greek and Roman education. Now, what was it about a self-governing free enterprise society that they realized that education was really important and everyone who had a vote had to be educated? How did you do that when somebody had to do the work? They understood antiquity. The way people got the time off to work was slavery. Ever think of that? So sure, you can't have a self-governed free enterprise society that requires education without slavery. Oh my goodness. Nobody ever told me that. Can't know what you don't know. So, 1854, Alexis de Tocqueville writes, when he comes to America, democracy in America, and he says, oh, what a shame it is that Americans enslaved a race. Slavery is temporary. If you enslave a race, you'll never erase the animosity. Is that today? Yeah, it is. That's today. But this whole curriculum, now, we don't study this anymore because why? Unlike the Pythagoreans, the later people didn't educate women. The Pythagoreans did. But the rest of it, and so we got the idea that classical education eliminated was just not for women. So, you know, today in this school, you talk to somebody about, well, let's study Western Civ. Oh no, that excludes women. That was the choice of the society. It has nothing to do with the value of the curriculum. So we must learn it. We must learn it. Okay, I'll quit preaching on that and we'll start on the rest of it. If you would turn in this page, we're going to go and quickly go through what Pythagoras said. All is number. They had a religion based on number. They knew that all of creation could be described with number, and they found something that was just terribly disturbing to them. And that was that nature could not be described with ratios of whole numbers. And that became the secret, because they didn't want to tell anybody that it couldn't be, because to them that was imperfect. That was imperfect. But we're going to take you through a little exercise that will let you learn this secret. Okay, the side length of square one is the radius of any circle. What in the world does that mean? The side length of square one is the radius of any circle. How long is that side length? As we say in Texas, it don't matter. It don't matter. It's just any radius of any circle you can call the side or the unit for square one, because you're going to harmonize from square one regardless what distance it is. You can see those two different patterns. two different square ones, but the harmony is the same, and you're going to learn how to harmonize. All right, this one's tough, especially for you math minds, because all your life you've had these visions of infinity, and I'm going to take them away. The root of a square is the length of its side. Will anyone argue? The root of a square is the length of its side. Oh, come on, somebody argue.
Well, they probably know that.
I know they know it, but I assure you, few people who hear this do. They can't go into the geometry behind algebra because nobody ever taught them that algebra describes geometry. You all figured it out before they told you. But do you realize that the teaching of algebra 1 before geometry prevents about 70% of your potential students from believing they can do math? Why would we do that? Anybody, why did we do that? And how long have we done it?
Algebra is considered the tools used to solve anything after it.
After what?
After algebra.
Well, why do we teach geometry after Algebra 1?
Because there are algebraic equations involved in geometry.
Certainly wasn't in 500 BC. There was not even a thought of algebra. It was simply geometry, geometry, geometry. So I want you to think about that as you go into your career. What can we do to get the geometric journey started and make the youngster want the tools that are there? Because they can teach themselves online. It's easy with the Khan Academy. They can be ready for calculus in the, 8th grade? If they just get it on a geometric journey, and that's what I'm hoping that we can do. Listen to this. Humans are not the only animals who build. Birds, beavers, bees, and ants build their habitats and nothing else. Humans are the only creatures we know of who manipulate ratios, proportions, fractions to improve their lives. Therefore, humans are identified as rational, reasoning beings. Isn't that simple? We manipulate ratios. That's what a classical education teaches you, to manipulate ratios to improve your life, both in 3 dimensions and in time. So simple it hurts. So simple. What you're going to do next, you're going to have to open those packets, and you're going to do this. You're going to build square one with 4 paper plates. Can you do that without explanation? First, you're going to fold it in half. Then you're going to fold it in a quarter. And then you're going to take your pencil and mark a line on each diameter. Then you're going to place them because those lines will let you line up square one. Turn to this section in your find out and do that. Tape it on the front and the back on the lines so they'll stay together.
All right, someone raise your hand and tell me the first thing he asked you to do. Because you're all getting in the paper plates, but I'm not sure everybody's on the same page. Raise your hand. What's the first thing we're doing?
Take your paper plate, fold it in half.
I want you to put your hands down. Listen to Preston. What did he say?
Take your paper plate, fold it in half.
How many?
Fold it once and then again.
But how many paper plates were you folding?
4 total.
4 total.
Actually, I want to go ahead and do 5 exactly the same way.
How many now are we doing? 5. We're folding them
Let me show you the easiest way to get it exact is to pinch it out here and then go to the middle. And then take your ruler and crease it. We want it creased hard. And we want to go ahead and make the quarter fold and crease it hard. Now, when you get all 5 into the quarters, stop. And be sure and use your ruler. Just use the edge of your ruler to press your crease. Press it on both sides hard.
5 into quarters. Good luck with that. Go, Sarah, go. Multitasking. Thing. Are we good with this table? Solid? Thanks, Brett. I was wondering how you were going to get them all. Are we good at this table? We're doing this? Honestly, you'll be sure.
Yeah, when you get 5 done in quarters, stop. Then we need to move on. Don't fiddle. We got a lot to do. Fiddle not.
You have
If
1
your neighbor's
minute.
having trouble, help them.
1 minute, 60 seconds to success.
Don't fiddle. Hurry. Are we on number 4?
No.
Are we on number 5?
That is exactly what Sarah did.
Everybody got 5?
Okay.
How many you own? Okay, hurry. Hurry, hurry. You got
30
lots to do.
seconds. Good luck with that. Got a good teammate here. If you do at least 3 though, you can pull them out. You can do all 3. It works.
Now, you remember to crease them. They gotta be pretty. They gotta be pretty. Okay? Now, let me borrow your pencil now, show them. All right. If everyone will look this way just a moment, let me show you how quickly you can mark these diameters. You keep your folds like this and just stick the pencil in there and draw a line and you got it. And then do the other diameter. Do that on all 5.
Robin,
Just fold it and just run your pencil through it.
what did he ask y'all to do?
Just mark your diameters on all 5 plates. Mark it like this. There you go. Crease it good. Not gonna break the other. It's pressing off that tape. This way. Real hard.
Do we know what we're doing on this one?
Okay.
I'm not sure if we're doing both directions just once.
Yeah, hold it. Mark it.
Are we supposed to do both directions with the pencil or just one?
Both
Circumference.
2 diameters or 1?
He said both.
Yeah, both diameters. All right. When everybody gets all 5 marked, tell me. And hurry. Good night, hurry. This is not hard. This is as simple as it seems. It's as easy as it sounds. Everybody there? Is there all creases pretty? Look at your neighbors and tell them how pretty it is. It's not pretty creases.
Beautiful.
Okay.
It just makes it really, you can't mess it up. All right, everybody there?
You said those 3, right?
Yeah, both diameters. Mark both diameters on 5 plates. Come on, man. As soon as you do that, look this way. Look this way. Look this way. Get close. Get close. One more diameter. One more. How's the special ed table this way?
We're good.
All right. Uh-oh, you're gonna have to get another pencil. All right, everybody ready? Everybody looking this way? I want you to hold this up and tell me how many names we have for this angle. What is this angle? A what?
Right.
Somebody said right angle? How's that opposed to a wrong angle?
Square angle.
Huh? What does that? What does right mean? Is that spelled with a W or an R? Huh? Why is it a W? I have a wheelwright, and that's spelled with a W. I'm confused. What else do we call it? Call what? A square? Well, it's part of a square. But give me some names for it.
90
Oh, wait, you said, is there some degrees related to it? What? What? 90 degrees, and it's a right angle. That's the same thing. Is it anything else? What? Quarter pi. What else? What is it, 3 hours? Is it 15 minutes?
Quarter.
Is it from north to east on the compass?
Somebody said a quarter.
A quarter? Oh, it's 0.25?
Sure.
What else? What else? I'm confused about this. Do you think any students ever get confused about the simplicity of 1 to 4, 1/4 of a circle? What about 25% of a circle? That's 0.25, isn't it, except for that funny thing on the back end? Now, how could kids ever get confused? All that is a quarter of a circle. Why don't we clarify that for them? We change bases easily. What if it's $1? Oh, 25 cents. And that's 0.25 either. Oh, I thought that was a percentage. Boy, that's confusing. It's just a quarter of a circle. Now what we're talking about is the very most common ratio that humans use to create. What do we talk about here? What is this? Why is it important? What a carpenter uses, framing carpenter. Everything we build to live and work in has 90-degree angles. Can you count the 90-degree angles in this room? We'll start. Where are they? Let's see. 90. Well, wait a minute. You mean that's just this circle folded twice? And it's all those names? It's so confusing. Wonder how many teeth there are on those different names. Think about it. It's just a quarter of a circle and you've just done it. Now, if you put all four of these pieces back together, what does this look like? Huh? What does it look like if you put 4 of these quarters back together? A circle. What if you reverse them? What does it look like? No. Think again. If you reverse them from the circle, what do they look like? A what? You mean a square has the same number of degrees as a circle? What a surprise. And you just taught it.
Where's the square, guys?
Where? See, the special ed table needs some help.
No, I think the other tables do too. Show them the camera. Show Robin. Let Robin show.
Okay.
I lost it. There we go.
Look at there, you put 4 of them together and you got a square.
What Robin did.
And all you've done is fold 4 paper plates and there's 360 in a square. Now how many, a triangle, how many angles are there in the, degrees in a triangle? How many? How many, okay, if this line is 180 degrees divisor of this circle, tell me something. If you fold that line anywhere twice, what have you done? You've made a triangle. You've just taught that 180 degrees is in every triangle, right? That's a pretty ugly triangle, because I don't make pretty points. But really, anywhere you fold that line, half a circle folded is a triangle. Therefore, it's 180 degrees. Is that easy to remember? Yes, it is. It's real simple, isn't it? All right, let's go back to the quarter. Now, the more you do the folding, the prettier it gets, I assure you. It is amazing how quickly you can learn to manipulate paper plates. They're wonderfully adaptable. When you fold them wrong, you can refold them correctly and they'll still work. The best paper plate for these exercises is from Dollar Tree. It's the cheapest thing there is. You want one that'll fold. You don't want one that's hard. Okay, everybody got a square? I want you to fold that square into this triangle. Fold that square into this triangle. Everybody got a triangle? Got a triangle.
Look at my square. I heard something track. I don't see it, but I heard somebody track. These guys are still in the dream team. Not me. I'm trying to do it. Oh, are you making a triangle? Yeah, another triangle.
Okay. Everybody got one of these?
Wait. Oh, you folded it?
Everybody got one of these?
Everybody got a triangle?
I want you to lay this upon square one and tell me what part of square one it covers. What part of square one does that cover? Would you call it a half? Okay. My question is, how do we double the area of square one to where we will have that yellow square, which is exactly double square one? How do we do it?
Very carefully.
You've already done it. Unfold your square and lay it on square one. You have already done it. Lay it on square one. 1, 2, 1, 2, 3, 4. Can you see that? 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. You've doubled it exactly. It's not 1.9999 forever. It's 2.
What?
Because geometry is precise.
What's
Pardon?
your 1, 2, 1, 2, 3, 4? What do you? 1, 2, 3, 4.
You use the diagonal, 1, 2, 1, 2, 3, 4. You use the diagonal of any square to harmonize a double of that square. And my gosh, nobody told me that when I was 12. The diagonal of any square will double the size of the next square if it's used as the side 2. That makes sense? Isn't that simple? And you just did it, didn't know it. We didn't talk math. We didn't talk infinity. We didn't talk never-ending fractions.
Not everybody at the table feels the same way.
This is the diagonal of the square.
The diagonal of any square is the square root of 2.
He is going to explain to this table.
Okay.
Because we still have some confusion.
Gotcha.
Side,
There you go.
but our new square is exactly double. So if you take the diagonal
Okay, you got
of the square and make it the
Square root of 2 is what you just
Side
square will
length,
be
got right there.
a square is
Everybody got it?
the next square.
Everybody understands square root of 2 is
So
the
fold it back
diagonal
in
of square.
all the way down to where it's half. Do you see where it's half?
Hey, did you see?
Okay, yeah.
Square root of 2
Now what
is
happens
diagonal
when
of the
you
square.
There you go.
explain the 1, 2, 1, 2, 3, 4?
You can look at the
Okay.
square part.
It's irrelevant.
You use that distance across it, it'll make a
Yeah,
square
that-
exactly
But you understand that you
the same.
have double.
Yeah.
It just didn't seem that at first.
Okay, everybody got the concept. The diagonal of square 1 is the square root of 2, always. How could we use that practically? I learned that from a plumber. How could we use that building? If the square root of 2, we know if you put your calculator, it's 1.414 to infinity, right? If you multiply it by itself, what does it come up to? 1.999 unless it rounds up. Because it's not precise. Indo-Arabic numbers have a failing. In that situation, they put us into infinity when geometry does not. Geometry is exact in doubling the square. That's what we're doing is harmonizing. Now how are we going to make the square 3 times as big? Okay, fine.
Let them think about, let them play.
Okay.
See if they can figure that
How
out.
are you going to do the 3 times? They're never going to guess it. I'm going to have to show them so you don't have that.
Yeah, okay.
They're never going to guess it.
Okay,
All right.
heads up.
Heads up. We're going to triple, quadruple, and quintuple, just like that. How are we going to do it? We know that the square root of 2 got us the double. What's going to get us the triple? Just logically, could it be the square root of 3? Or the square root of 4? Or the square root of 5 to get the harmony? How are we going to get those on a paper plate without any math? We're going to use the magic. We're going to put 2 plates together and it's going to jump out at us.
You got your projector.
Tape 2 plates. Tape 2 plates together, just like you did when you started with the 4. Two more plates. Do 2 more plates exactly as you did in quarters. Mark the diameters, and we're going to show you some magic that the Greeks understood 2,500 years ago, but we have forgotten it. Okay, good. Good. So, we've done nothing but the same fold in all of this. Nothing but the same fold. Now, can a 5th grader do this? You should hope so. Okay. You should hope so. I hope so. I think I could have. But we've introduced square roots without talking about infinity or numbers. We're just folding plates, having fun. Okay, same fold. Remember your pencil. Mark your diameter. And tape 2 of them together, just like half of your other 4.
Oh, yeah.
I mean, a lot of it's square, but I do believe
Okay, tape them together front and back, just like you did before. I really should be doing something myself.
tape it together like this.
How you doing, Randy?
Everybody there? Got two plates together?
We're just taking two. I don't know what your bedroom was. I was gone. I still have so late, so
It's gonna be like this.
which isn't it late? I am, and I know, but the fact that I knew I was gonna have to wake up early and study some more. I didn't even wake up.
Okay, got two plates together. Almost. Almost.
Yeah, I had the last semester meeting.
Monday, Wednesday, Friday, I have completed biology, that is just basically a statistic.
Is that your 300 course? Is it 300 or 400 course? I had to take 2 on the biology.
Thanks.
Okay, everybody got it?
I feel like I should put arts and class project.
How are you doing? Paper plates are all done? There's
Anybody need help over here?
We good?
I'm gonna get like some really good ones. So I think that really helps me. I think if it was just no matter what.
All right, are we ready for the next step? Everybody got two plates? Magic is about to occur. Magic is about to occur.
Deep breath.
I need a ruler. Bar, okay. All right, I'm going to get back on the screen. I want you to very carefully make a mark from the point where the circles intersect, top to bottom. Exactly where the circles intersect. You see where that is? Folks, let me tell you, there's magic there because that's the square root of 3. If you use that as the side length of the square root for the blue square, it's exactly that long. How could that be? How could that be? We know that the diagonal of any square is the square root of 2. The divisor of any angle on an equilateral triangle is the square root of 3. How can that be? Now where's the equilateral triangle here? You've already defined it. If you go from the point where I've got my finger, go through the center to the diameter, you've created an equilateral triangle. Go ahead and draw it on there. All right, let me show you. It's already there. It's just magic. You go from that point right there through the center of the circle. Everybody doing that? Look here. Go all the way there and go way over here through the center, across, and guess what? You can go across the bottom and it'll go exactly through the intersection of the bottom of those two plates. Isn't that magic? Now, why would the bisector of any angle in an equilateral triangle be the square root of 3? Can somebody tell me that quickly? Use your Pythagorean theorem.
What was the question? Did somebody repeat?
Why is the bisector of any angle in an equilateral triangle always the square root of 3? Use your Pythagorean theorem quickly.
All the sides are the same and the base split is half, so the hypotenuse is going to be 2. So.
Okay, speak up. Walk them through it. What does that mean? You know algebra. 5th graders don't, so let's do it. Let's use our algebra and see why that's the square root of 3.
Equilateral triangle, all the lengths of the sides are the same. So if we split it, the base is going to be 1. The hypotenuse is going to be 2. So the other side's going to be square root of 3.
Yes.
Oh.
Everybody got that?
They're smart.
Now say that again. That's not coming across. This is where I lose people. Even math people.
Hey, David, stand up and show you.
Yeah, point to what you're talking about. Point to, yeah.
Because you are explaining it well.
All right. He's drawn an equilateral triangle. So these lengths right here are all the same.
Yes.
All right.
That's 2.
Has everybody got
the
the equilateral
length of the
triangle?
square one is the radius of any circle. You've got 2 circle radius there.
So if we split it, then this one right here is split in half. So I've got length 1 here and I've got length 1 here.
Right.
So by the Pythagorean theorem, if this is length 1, we know this is length 2. This has to be square root of 3.
Y'all see that?
Now, somebody doesn't see it, and it's okay if you don't. Let's keep talking
Do you
till you
see it,
see it.
Haley?
It's very important that you understand it. Very important. Thank
I
you,
see
sir.
where the length 1 is.
Okay,
Okay, this is length 1.
Right.
that's 1.
And this is 1.
So what is,
Oh, so that's 2.
no, but you're eliminating half. You're looking at this triangle right here.
Yeah.
All right,
So
here's
what's
your
the
right
length of
angle.
the-
This is A squared, this is B squared, this is C squared.
Right.
What is this? 1? What is this? We don't know. What is this? We know that's 2. C squared is 2.
You can see that that's
C squared is 2, so that's 4. 4 minus 1 is 3.
So the
4 minus 1 is 3. You got it? Everybody, 4 minus 1 is 3. Has everybody got it?
This is the one. I can see the two.
Okay.
Radiuses.
We know where the square root of 2 is. We now know where the square root of 3 is. Where's the square root of 4? It's the easiest one. You fold it the first time, it's the diameter.
It's the whole diameter, yeah.
Isn't that smart? Because what? 2 times 2 happens to be the diameter, doesn't it? Everybody got that? All you got to do to make the sine of square 4 is fold the diameter. That's the length of it. Now, where are we going to get the square root of 5?
Should they label the square root of 3? Maybe that would help them.
Absolutely. Go ahead and write the square root. In
Y'all know where the
fact,
square
you
root
can
of
do
3
that
is?
you can do that in color. And I'm
Which
about
one-
to show
which
you
part
what the
square root of 3?
5 is.
Square root of 5 is long.
The diagonal, listen up, folks.
Wait, should I do it?
Where's your whole triangle?
talking.
The whole triangle is new, right? Where's it cut in half? Where's it been bisected? Okay, so which
Because you mentioned
two triangles are your
Pythagorean
equilateral, I mean, your two congruent triangles? Here and here, right? Which side is it just a side length of 1? Do you know? David, show our
That is
hand.
easy. That's where we're headed. You're the only one who noticed what we're doing.
Okay, well, I was looking at this and I was like, wait a minute.
No, I didn't draw the triangle on there. See, what I'm taking, that's just the end result. So you can fold that and have the harmony.
Okay.
See, that's how you make your side lengths. I didn't want to confuse you with all of this. Okay. Everybody got the, understand the square root of 3?
Where's the square?
Now, we got the square root of 4 because it's the diameters. Everybody understand that?
Square root of 3 is that whole thing?
It's the
Yeah,
whole
square
middle.
root of 4, that's the side length of your 4th square.
Right.
The 5th square is kind of magic, and here's the deal. Everybody listening? Anybody listening? Nobody listening? We got table 4 over here, not listening. Okay, here's a simple statement. The diagonal of the double square is always the square root of 5. So run your, imagine you had a square, you squared off the circle. Your double square is right here. Let me get over here on
Yeah.
It's where the diameters, it's where the diameters would fill in to make a square there and a square here. Now, let's go across from the diagonal of the double square and use our Pythagorean theorem again, and what we're going to get, we're going to find out that the diagonal of the double square is always the square root of 5. Why is
Where
that?
did you draw that line from to?
From the top of the one diameter to the bottom of the other.
Okay.
That's a double square. You look on the back, you can see that's the double square. It just doesn't have the top piece or the bottom piece on it.
It's not more
Does that make
like.
sense? See, if I drew a line right there, that'd be a square and a square.
Oh, look at how precise that is. It even
gonna
right
go
through that
from-
process.
Now, all right, Pythagorean theorem. Why is that the square root of 5? Here's your right angle. Here's your right angle. You know that this is 2. Anybody listening? You know this line is 2. Here's your right angle. This line is what? 1. So 2 times 2 is what? Plus 1.
5.
C squared is 5. So what's C? It's got to be square root of 5. Isn't that amazing? Pythagorean theorem is important, isn't it? It's important because you have just learned with these paper plates how to make that emblem. You've got the 5 links. Have you marked them? Let me show you how it's marked. Now notice this is a smaller plate. You can buy 6-inch plates and the end result is smaller and it's easier for kids to manipulate. But This is the key. Two circles together hold all the information you need to make that beautiful, harmonized envelope. Now look at that. It's confusing, doesn't it? See, because I've got a pentagram in there. Why? Because I'm going to show you how to make this. Now, what are the regular solids? Describe that to me. Speak up. The regular solids, how many are possible in 3 dimensions? How many are possible in 3 dimensions? The regular solids. Anybody ever heard that?
A cube.
A cube is one of them. What are the others? How many are there? Well, how many sides does a pyramid have?
6. No. 5, 1, 2, 3, 4. 4.
Well, if there are 4, it's a triangle.
Yeah, pyramid's 5.
But it's got a square on the bottom, unless it's half of an octagon. See, we don't talk shapes. We're going to make shapes.
What's the shape of the base of the pyramid that you want?
The base of the pyramid that I just want to know how many possible regular solids. What does a regular solid mean? You got the same polygon creating a volume without gaps. How many can be made in 3 dimensions? Now, 2,500 years ago, anybody who was educated understood this because it's simple, but we forget it. It's too simple. There are only 5 regular solids possible. They are made of equilateral triangles, one of them is made of squares, and one of them is made out of pentagons. That's all there is. Multiples of 2, 3, and 5 build nature. We forget to tell people in science it's that simple. Multiples of 2, 3, and 5. And when you understand the square roots of 2 and 3 and 5, you can imitate nature. That is the beginning of science. But we get confused and lose our simple geometry and get lost in infinite, never repeating decimal fractions that scare people. We don't scare people with geometry. We have fun with geometry because we imitate nature. We create beautiful things. It's so simple, folding paper plates. Now, we're not going to go through the harmonizing process, but let me show you from this little piece how this works. Now, I have done this in yellow from my center point here. This is the side of the yellow piece. Everybody agree? Yeah. That's the diagonal of the square. We know that the divisor or bisector of the equilateral triangle is going to be the side of square 3. Would everybody agree that that works? We know that the diameter is going to be the side of square 4. We know that the diagonal of the double squared, my gosh, look at that, it's going to give us 5. Can everybody make that now? Does it make sense? Can a 5th grader do it? Now, what if you started to tell them the math they just learned? What did they learn? What they learned? They learned the Pythagorean theorem. They learned rational and irrational numbers and the value of an irrational. That it's a line length. It's not an infinite decimal fraction. What else did you learn? You learned square roots. Now, where does that come in the textbook? Especially if we teach algebra and then geometry. Folks, that's cruel. We don't need to do that. We need to start a geometric journey earlier and let them grab math. Demand it. Get it off the internet. Teach themselves. Now, we're not going to, can you all do that on your own? Get colored paper and make that? That's the goal of this course, is to make that and then take you into the regular solids, because everything you need to build all of these, and these are the regular solids. Now we're going to have to learn to fold from a paper plate, perfect tetrahedron. There's nothing, we never cut a plate. We never use a ruler except to fold. All we need is what's in the circle. By golly, look here. The largest volume nature can make is a sphere. We live on one. The moon is one. The stars are one. That's all the information that nature can make is in a sphere. All we've done is let the air out of that sucker and put it in a circle. Didn't lose any information. That's why we can build nature without any outside information. It's all in the circle and the two circles put together. Isn't that simple? Don't you wish you'd learned that when you were 12? What would you have done? All right. Those of you who folded that fifth plate, can you find that fifth plate? All right, this is really hard because I want you to take let's see, 4 of you. We need 2 more of these. So you and you make some more. Because we're going to lay these down, we're going to tape them together, and you know what we're going to have? We're going to make this. We're going to imitate where we live in a hexahedron. But what was that, about 90 degrees? That's what we make to live and work in. We're going to take 6 of these, and we're going to lay one in the middle, and we're going to put a piece of tape on all 4 sides. We're going to lay it down like this, put a piece of tape on all 4 sides, and then we're going to turn it over, and we're going to put 4 more plates around it, and then we're going to put one at the end. We're actually going to make a cross out of it, and then we're going to fold it up into a cube. Has everybody got that in your mind? Let's do it quickly, but we're running out of time.
How many of these do they make?
Well, how many sides does a hexahedron have? Hexa is 6. We got to have 6. 6. You got 3 here. You got 4 there. You got 4 there. You need 6. Make them exactly the
Why
same
don't we
way.
make one per table?
One per table.
Rather than per person?
Okay.
Y'all already
No,
have,
no. I want to make 1 cube per table. Yeah. Just get 6.
so you just have to make 2 more.
You just make
3 more.
3 more.
Just make 3 more.
Right.
You only have to make 2 more, because you already had 4 made.
Now, when you start to put them together, you'll find out that the
You already
lines,
make 1 per
the
table?
edges
You
are
already
not
had 4?
straight.
Let's make 2 more. We're square. We're in a square. Good. It'll work.
Now you take it.
Oh, good. All right, here's one that's getting way ahead here, folks. She is going to win the prize. She is going to win the prize. Now, if you'll raise your right down, put tape on 4 sides. Put tape there, and then lay your plates on the side. And make one on each side, and one on each Actually, no. Here's the piece. Put
Close enough.
Four ways around it, and then add one to the other end, and then when you lift them all up. Now, just lay your plate. Now notice when you lay it, they don't get much.
Oh, I heard you just
Okay.
came off earlier today.
Because it works fine, you just make it tough. But use a little room to put it, plate there, and then fold it
Make
up.
this the crossings go your shape.
Okay, everybody got a cube? Oh, you're doing great. Doing great. Okay, this, we have made the hexahedron or cube. And just think, everything we build is either a cube or an elongated cube. It's where we live and work.
That one you want, yeah. It's not perfect, it's not going to be perfect.
It is a lot not to be perfect.
One job. Okay, look, isn't that a pretty thing? And notice those tabs you've got to hold to make your tape fit good. Isn't that neat?
Got one.
Got a cube? Got a cube. Well, isn't that pretty? Now you got that. 2 more here. You're okay there. Just put 2 more here. Okay, now we've got to do something really hard. We've got to learn to fold the tetrahedron, and we've only got 22 minutes. So get your cube. Don't take the time to make it perfect, because when you're doing it for your final display model, you'll want to fill in the whole lines to take. But don't do that now. We've got more to learn. We've got to learn how to make the tetrahedron, because this folds and the square fold are all we're going to need to build these solids. And plus we're going to get that pentagon started somewhere. But when you make two of these, it becomes this. Tetrahedron to octahedron. Just the same fold, two plates instead of one, and it's magic. It's magic. Now, this is the first volume possible in 3 dimensions. Why? You're raising a point above a triangle, and you're making 3 more triangles. Therefore, it is nature's strongest structure. If you were to hit your hand on it, it would cut it. That's a paper plate. The strength of the tetrahedron is what makes nature strong. Carbon. Who is our chemist? What's tetra mean in chemistry?
Tetra.
Tetra means what? It has what? It's all it is. What is carbon? It's a tetra. What's a diamond? It's a tetra.
All of the big
So
structures.
all of structure in nature comes from this basic geometry. We don't teach it that way. Now, this is the largest volume that nature can make. You could say that's the greatest enclosure with the least exposure. So it's not strong, it's squishy, isn't it? It's not supposed to be strong. But it is the largest volume. This is the smallest volume nature can make in 3. It is the least enclosure with the most exposure. Isn't that something? Isn't that simple? All of nature is between the tetrahedron and the sphere. All the pieces. And that's what we're making is the regular solids. We build from the tetrahedron. We fold 2 plates and we make the octahedron. Put them together. All right, we're not going to do that. We're going to jump onto the icosahedron, which again is equilateral triangles. There's 20 of them. It takes 6 paper plates because you're going to cheat on it. You're going to cheat on it because you're going to fold this thing 3 times and overlap 3 of the petals. And that's going to make half of it, then you're going to make half, and you're going to put 2 halves together, it's going to look like this. Now, we've got to learn how to fold the tetrahedron, and we're going to do that real quickly. Get you a plate folded in half. You don't have to mark it. You don't have to mark it. Since I have this wonderful machine over here, this is going to be real easy. Real easy. And as I tell the kids, fold it and smiley face up. When everybody's smiley face up, hold it. Everybody get it? This is easy. This is easy. Now, listen carefully. We're going to fold it, but we're not going to crease it. I'm going to show you what we're going to do. We're going to find the middle of that diameter. Look at the screen. I'm going to put it like I'm going to make a quarter, but I'm not going to crease it. I'm going to pinch it, and I'm going to open it up. You see? Pinch it. Why don't you just mark that center? Just mark it there, so you'll know right where it is. Now, don't fold it. Don't make it into quarters. All right, everybody got the mark, smiley face? Look at the board. Watch what I do with my thumb. I am going to put it on that mark, and I'm going to fold this over, and I'm going to try to balance those triangles. And I'm going to cheat. I'm going to start counting these bumps. 9.5 bumps, you're right in the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9.5, and I'm going to crease it. Look at that. And I'm right in the middle. All right, everybody got that? You've got 2 flaps and you've got 1 flap. You're going to take the 1 flap and fold it back to the other side and make a triangular pie piece, which will divide that circle into 6 parts. Open it up and count them. If you have more than 6, you've messed up. Everybody got that? I go back through it. Smiley face. Mark. Fold over. Fold back. Circle.
Yeah, I did too.
Fold over. Fold back. Pie piece. Everybody got it? Everybody got this?
Yeah, I did wrong last time.
Nope. Okay. Here is what not to do. It is easy to do. This is what not to do. We want this.
Okay, guys.
We want this. Not this. All right. Here's how you do it.
Unfold it.
Just split this piece and this piece the same size. And then half, 1, 2, 3, 4, 5, 6, 7.
About 9.5.
Okay, you guys have it?
I don't think they I said what I would.
Now, folks, if your back flap is not perfect, it does not matter. That's what's wonderful about doing this with kids. It doesn't have to be perfect to work. You got 6 5-pieces? No, you don't. Yeah, you do. You're good. All right. Now, it's good to crease it. It's good to crease it good. Now, has everybody got 6 5-pieces, not 11?
I know. I don't need it, Wyatt. No,
6 5-pieces. Look my way if you got 6 5-pieces. Look my way if you got 6 5-pieces, because I'm going to direct you to the board for the next step, and it's real important, and we've only got 14.5 minutes. Let's go. Come on. Everybody ready? Now look carefully. I'm going to take preferably the original diameter if you can figure it out, and I'm going to take where it intersects with the circumference and fold it to the middle, and I'm going to crease it. Be sure you're on the diameter and you're taking the diameter to the center. Take the diameter to the center. Everybody got that? Turn it around to where you see another diameter and take it to the center, making sure you have a pretty point out here, because you're going to make an equilateral triangle. That's all you're doing. When you see the last piece, you fold it over, don't worry about the center, you just make pretty points, and you've got a beautiful equilateral triangle. Everybody got that? Be sure and crease it. Everybody got an equilateral triangle. Worry about the points, don't worry about the center. It does not have to be perfect to work well. Oh, look at here, hold that up. She's found it. There's her tetrahedron. You fold a point across to the other side 3 times and you've got a tetrahedron. Wow.
Then you'll have points across to make sure equilateral. Got it? You should have a cone.
See what I'm doing? 3 times I'm folding that sucker over.
It's not taking.
You don't want to cone anymore.
Show me the 2 X's we put points.
All right, look at that, folks. That is a beautiful tetrahedron, and you can go ahead and tape it. And then do 2 more to make your octahedron.
Up to the center?
Okay, you're going to take any point, go to that
center of the
middle over there,
Okay.
and crease it.
Yep.
Oh, you fold
You're
yours
just
out.
looking good. Be sure and crease it good. Look at that. Isn't that amazing? All that information.
In theory, you have. In theory, you have.
Looking good.
What is that? The ones the other day looked.
Each of your
There you go.
vertices
And go across.
to make a, yeah, to have a joint.
Sorry,
Right.
you have a nice point one.
Let me show you how you make the octahedron. It's simply taping these 2 together. And notice that you've got a familiar 4-sided pyramid that is mirrored.
No.
Of course, you have to tape them to make them
Open and
stable.
accentuation.
But you see how that makes the octahedron? The 8 side out of the 4 side. All there is to it. Okay, everybody got the tetrahedron?
And how does it affect the cell?
All the organelles are cells.
Isn't that cute? Crazy. Now, feel how strong that is.
Are we taping it together?
Yeah, go ahead and tape it. Go ahead and tape your
Yeah,
tetrahedron.
down until to each center. Good. I love that. Do the other one. You need no ass. It's okay.
Isn't that pretty?
Now, when you open this up,
You
you'll
did
see now you fold these up. So they make it
Okay, tetrahedron. Everybody got it? Look at that. Now, is yours taped? Let me show you. Let me show how they go together to make the octahedron. You just tape them together, and all of a sudden you've got that beautiful octahedron out of 2 tetrahedrons. Isn't that neat? That's the second solid that's possible. Okay. Now, I need 2 that aren't taped.
There you go.
All right. All right, everybody look up because we're running out of time. We're going to show you how to make a Heads up. You take 3 of these and you overlap 3 flaps. Take that sucker together and you've got half of the icosahedron. That's 20 equilateral triangles. You see how you just take 1 flap and overlap and tape? You're actually hiding 2 flaps, and you're making half of this. And you make 3 more, and you take this together, and you've got this solid. All right? Now the next step is, we do not have time to show you, but you can go online and see how to make a pentagon. I'll find it. Pentagon. And I drew the pentagon here on the plate because you can lay the next plate on it and do that 12 times and mark the 5 points. You do just exactly like you did with the 4 points. You take the 5 points and fold them just like you did. There are tabs in there, and you take 12 of these together. Now folks, this has all been in the circle all your lives. We haven't used anything but circles, tape, and a straight edge and a pencil. And we have created the solids, the only 5 solids. Now, a regular solid means if you put a sphere around it, every intersection would touch the sphere. And there's only 5 possibilities in 3 dimensions. Everybody got that? And you created it because it's all in the circle.
I've seen them called the platonic solids.
That's the platonic solids, but there are examples of rock solids 1,000 years before. That's an octahedron.
Yeah, this is a piece of fluorite. It crystallizes in cubes and it cleaves in octahedrons.
Everybody listening?
This is a piece of fluorite that crystallizes in cubes, but it cleaves in octahedrons because of the crystalline structure.
Right. Crystalline structure is just what we've done. That's how nature builds. Nature has a problem building 7 because it's not a multiple of 2, 3, and 5. It doesn't mean it can't, but you don't see it in 3 dimensions easily because it's not a multiple of 2, 3, and 5. And the square roots of 2 and 3 and 5 and understanding them will help you imitate nature in art, architecture, and we must talk about music, number, and time very briefly. All right, I need a volunteer. Who are our musicians? Okay, come up here. I need help. The Pythagoreans understood. I need you to hold this up where they can see it. You hold this in there. Yeah, I gotta play this thing. I don't have to stand on my head. All right. The Pythagoreans noticed, or Pythagoras is credited for noticing, that if you divide a string, now there's 2 strings here. They're supposedly the same substance, same length, same tension, and they should have the same note. You're going to hear that they don't have exactly the same note. They don't. Can you twist that to make it, tune it a little? It doesn't matter what note, just make them sound the same sound. Are you good at tuning? You know, there is an app that'll do it exactly.
Yeah, there is.
All right, let's assume that's the same sound. What we're going to do is take half of that. Now, the Greeks understood the basis of Western music was the ratios of 1 to 2, 2 to 3, and 3 to 4. Now, that other sheet of handouts, flip over there until you see the piano key, and it'll explain this a little bit better. 1 to 2 is what I'm going to show you. We're going to play a full string against a half a string. And what are we going to get? You're going to get your first harmonic. You have got the octave, and that's what an octave is. How many notes are there in Western music? How many notes are there in Western music?
7.
Whoops.
Octave. 8.
Can only be 7 because the octave is either twice or half. That's the 8th note is twice or half the first note. So there's only 7 notes. So what we've done here is created 3 of the notes. The octave. If we go 2 to 3, what is the note we've created? 2 parts. Once again, we've got harmony. What is that? That's the perfect 5th note out of 7. Look at your piano. That's what the 5th note is 2 to 3. 3 to 4 is an inverse of 2 to 3. It's the 4th note in the piano. Again, it's harmony. The rest of the harmonies are derived by something I haven't told you. It's the when you put the two plates together, if you were to draw the plate that's hidden, you would create an almond shape. Can you all visualize that? That's called a vesica piscis. That's Latin for fish bladder, is all it means. That's a fish bladder. The divisor of the fish bladder is what? The square root of what? What is it? You just got it on your plate. It's marked.
Square root of 3.
The square root of 3 is the divisor of the fish bladder. Now, in Renaissance art, the almond, or the vesica piscis, is extremely important. You see it all over art. And it's not accidental. It's a result of understanding the simple Greek geometry. All right. 1 to 2, 2 to 3, 3 to 4 is number and time. Look at this. All you need is that compass, marking device, and straight edge to create all the notes in a 7-note Western music. You can see on this that you've made a larger vesica piscis by increasing your radius, and you end up walking those links into the last circle to get it in the same octave, and you've created the exact lengths of strings for a 7-note lyra, or the hole placements in a wind instrument. And you've not had any measurement. You've just used your brain and the tools that we did the harmonizing over there with. You may put that down. Thank you so much. One other thing, because we got 4.5 minutes to get into magic, and that is this most common ratio of nature is 1.618 to 1. Whoops. It's not going to stay, is it? 1.6. What do we call it? The section, the extreme and mean, the golden section, the divine proportion, the godlike proportion, the divine section, the contingent section, the medial section, the golden cut, and in the 20th century, pi. All of you familiar with that? Why? What's it got to do with Fibonacci numbers? Huh? What's it got to do with fractals? What's it got to do with self-similarity? It is all of those things. It is the most common ratio in nature. Unlike the most common ratio of creativity of humans, which is rather mundane, it's at 90 degrees. There's not a single 90-degree angle on your body. But there's plenty of these. Take this little dumpling right here, and let's have an example. Would you stand with your back to this crowd, or are you afraid of it? Okay, sit. Face forward. I want you to hold your arm out, look like this. The other one. There you go. I want to show you something. You've been looking at the golden ratio all your life. If you look at this portion of your finger, if that's 1, this distance is 1.618. If this is 1, this is 1.618 of it. If this is 1, down to your wrist, this is 1.61. If you go from the fingertip to the elbow, the wrist is 1.61. And if you were to stretch from here to here, it's all over you, folks. Been that way all your life, and nobody told you. And that's golden mean caliper. Let me show you something about a 5-pointed star. The Pythagoreans wore a 5-pointed star for their identification, and there was a good reason, because every intersection on a 5-pointed star is at that golden ratio. Where do we see stars? Would you hold this up for me? Sure. Just,
We're all seeing stars.
Right, hold on. Now watch this. Look at this. Every intersection is at the golden ratio. Where do we see stars? 5-pointed stars. Now, a real star is just a dot in the sky, isn't it? But when you ask the kid to draw a star, it looks like this. It's the golden ratio. Where do we use them? How many flags do you see a star on? What do we put on General shoulders? What's the name of, what's that football team that's got stars on its helmet? What's that hockey team? Where do we see stars? We like stars, don't we? Why? Because it's us.
Well, no, they're pleasing to the eye because they're
Because of that ratio.
They're familiar on the eye, because it's all over us.
They're aesthetically pleasing.
So what we have done, we have pointed out humans' most common ratio of creation, and we have discovered, oh my goodness, nature has one that's so predictable, it's ridiculous. Every living thing has golden ratios all over it. When humans understand this, the use of this ratio and the use of musical harmony and put it in a structure, what happens? You call it a Gothic cathedral. That's what they are. And that's where Freemasonry started. Was the guilds that built Gothic cathedrals. Have we made a full circle? Folks, this is so simple. Anybody can learn it. But we have complicated, we are mired in minutia when it comes to math. We are mired in minutia. Can we do better? Can we do it more simply? Can we have fun with it? Can we have a geometric journey that will teach a youngster, gosh, I got to have this math so I can go do science. Science is just understanding how nature is structured and how we can manipulate what? We can manipulate proportions, fractions, to do what? To make our lives better. That's all we do. Folks, there's about 4 more hours of this that we don't have time for, but it's all fun. There's a bibliography in the back of that second handout. There are books over here. Y'all go do what you want to do, and I'll be around after that, and we'll, if you want to talk some more, we'll talk. Thank you.
They all need to know what's behind the red curtain.
Oh no, I forgot the secret. Now, have y'all, now y'all swore you wouldn't tell. You still there? All right, this is it. This is it. This is the most secret construction of the Pythagoreans. Is that familiar to you? Woo! That's what it looks like when you use a compass, and that's what the Pythagoreans did. Isn't that neat? But I didn't scare you with that first. For years I've scared people with that, trying to explain it. But when I figured out, do it with the plates, it's fun. And show them the beauty of harmony. I even got to Don with Magic Man. That's online free.
How long is Donald?
The part that you wanted to show.
Well, let me just show you this little last
Have y'all
section.
seen Donald Duck and Magic Land?
No.
You're going to watch it.
I will practice.